Hello there, and welcome back to the Sleepy Astronaut, where wonder meets wandering thoughts and science becomes the gentlest companion for your journey toward rest. Tonight, we're diving into something truly extraordinary, something that surrounds us every moment of every day, yet remains completely invisible to our senses. We're exploring Earth's magnetic fields, that remarkable hidden shield that has been protecting our planet for billions of years, quietly working behind the scenes like the most dedicated guardian you've never met. Before we begin this peaceful expedition into the invisible forces that cradle our world, I'd love to know where you're listening from tonight and what drew you to this particular corner of curiosity. Are you perhaps lying in bed, wondering about the unseen forces that dance around us? Or maybe you're settling into your favourite chair, ready to let your mind drift through the cosmos, while your body finds its way to rest. If you find these gentle journeys through science soothing, if they help you unwind after a long day, or simply satisfy that beautiful human need to understand our world a little better, I'd be ever so grateful if you'd give this video a like. It helps this quiet space reach other curious souls who might need a moment of wonder before they sleep. And if you haven't already, consider subscribing to join our growing community of dreamers and thinkers who find peace in the patterns of the universe. Now, I do hope this exploration is fascinating enough to engage your mind, but gentle enough to let you drift off peacefully. After all, there's something rather poetic about falling asleep while learning about the forces that keep us safe, the invisible embrace that has sheltered life on Earth since long before we arrived to ponder its mysteries. So settle in, take a deep breath, and let's begin our journey into the hidden world of magnetic fields. Because tonight we're going to discover how our planet became the most perfectly protected home in the solar system, wrapped in an invisible cloak that deflects dangers we can't even see. Imagine for a moment that you could see magnetic fields the way you see light. Picture stepping outside on a clear night and instead of just stars and darkness, you'd witness the most breathtaking aurora of invisible energy streaming around our entire planet. Vast ribbons of magnetic force would arc from pole to pole, creating a shimmering dome that stretches far into space, pulsing and shifting like a living thing made of pure energy. This isn't science fiction, this is happening right now, all around you. Earth's magnetic field, sometimes called the magnetosphere, extends thousands of miles above your head, creating a protective bubble that shields us from the constant stream of charged particles flowing from the sun. It's been there your entire life, working tirelessly without fanfare, deflecting cosmic radiation and solar wind like the most elegant, invisible umbrella ever conceived. But here's what makes this story truly remarkable. This magnetic shield isn't just some passive barrier sitting there doing its job. It's dynamic, alive in its own way, constantly responding to changes in space weather, flexing and adjusting its shape, sometimes weakening in one area while strengthening in another. It's a dance between our planet and the cosmos, a delicate balance that has been maintained for billions of years. The source of this invisible protection lies deep beneath your feet in the very heart of our planet. Nearly 2,000 miles below the surface, in Earth's outer core, liquid iron churns and flows in massive convection currents. These currents, driven by the planet's rotation and the heat from the inner core, create what scientists call a geodynamo, a natural generator that produces our magnetic field. It's rather like having an enormous dynamo spinning at the center of the Earth, generating the magnetic energy that reaches out into space to form our protective shield. But unlike a simple dynamo, this is a system of staggering complexity, influenced by temperature differences, the planet's rotation, and the intricate dance of liquid metal flowing in patterns that would make the most elaborate choreography look simple by comparison. What's truly fascinating is that this magnetic field isn't uniform or perfectly organized. It has personality, character, moods, if you will. The field lines emerge from the Earth near the South Pole and curve through space before diving back down near the North Pole, creating loops and whirls that shift and change over time. Sometimes the field strengthens, sometimes it weakens, and occasionally it even flips completely, with magnetic north becoming magnetic south and vice versa. These magnetic reversals have happened hundreds of times throughout Earth's history, roughly every few 100,000 years, though the timing is far from regular. During these reversals, which can take thousands of years to complete, our magnetic shield doesn't disappear entirely, but it does become more complex, with multiple poles appearing and disappearing as the field reorganizes itself into its new configuration. Now you might wonder, how do we know all this about something we can't see or feel? The answer lies in one of the most beautiful detective stories in science. We've learned to read the magnetic history of our planet by studying ancient rocks, particularly those formed from volcanic lava. When lava cools and solidifies, tiny magnetic minerals within it align themselves with Earth's magnetic field at that moment, creating a permanent record of the field's direction and strength. By studying these magnetic signatures in rocks of different ages, scientists have been able to reconstruct the story of our magnetic field going back millions of years. They've discovered that our field has been remarkably stable for most of Earth's history, with only occasional reversals and gradual changes in strength. It's like having a library written in stone, each rock formation holding a chapter of our planet's magnetic biography. But perhaps the most enchanting aspect of Earth's magnetic field is how it reveals itself to us in moments of extraordinary beauty. The aurora borealis and aurora australis, those dancing curtains of light that grace the polar skies, are actually our magnetic field made visible. When charged particles from the sun interact with our magnetosphere, they're guided along the field lines toward the poles, where they collide with atoms in our atmosphere, creating those ethereal displays of green, blue, and red light. In a way, the aurora is our planet's way of showing us its invisible shield, a gentle reminder that we're protected by forces far greater than ourselves. Those shimmering curtains of light are love letters from the cosmos, written in the language of magnetic fields and painted across the sky in colours that seem almost too beautiful to be real. The strength of our magnetic field varies from place to place around the globe. It's strongest at the poles, where the field lines converge, and weakest at the magnetic equator, where the field lines are most spread out. This variation has practical implications for everything from compass navigation to the operation of satellites and power grids. Animals have known about these magnetic variations long before humans developed the instruments to measure them. Many species, from sea turtles to migratory birds, use Earth's magnetic field as a navigation system, sensing the subtle changes in field strength and direction to guide their epic journeys across oceans and continents. They carry within them a magnetic compass far more sophisticated than anything we've yet created, an innate ability to read the invisible map that surrounds our planet. Sea turtles, for instance, use magnetic signatures to navigate across thousands of miles of open ocean, returning to the exact beaches where they were born decades earlier. Migratory birds can sense not just the direction of the magnetic field, but also its intensity, creating a three-dimensional magnetic map that guides them on their seasonal journeys. Even bacteria contain tiny magnetic crystals that help them orient themselves in their microscopic world. Recent discoveries have revealed that our magnetic field is currently undergoing some interesting changes. The field has been weakening gradually over the past few centuries, losing roughly 10% of its strength over the last 200 years. There's also a region in the South Atlantic where the field is particularly weak, an area scientists call the South Atlantic anomaly. These changes have sparked curiosity and, in some cases, concern about whether we might be approaching another magnetic reversal. While the evidence suggests our field is indeed changing, predicting exactly what will happen is like trying to forecast the weather for next year, fascinating to consider but extraordinarily complex to determine with certainty. What we do know is that our magnetic field has been our constant companion throughout the entire history of complex life on Earth. It's been there through ice ages and warm periods, through the rise and fall of species, through every sunrise and sunset that has ever graced our planet. It's a reminder that we live on a dynamic, living world, one that has been carefully maintaining the conditions necessary for life to flourish. The more we learn about other planets in our solar system, the more we appreciate how special our magnetic shield truly is. Mars, for instance, once had a magnetic field but lost it billions of years ago, leaving its atmosphere vulnerable to being stripped away by solar wind. Venus has no global magnetic field at all, and the difference in habitability between these worlds and our own Earth is striking. Our magnetic field isn't just a scientific curiosity, it's one of the fundamental reasons why Earth became the cradle of life as we know it. It's been quietly doing its job for billions of years, deflecting harmful radiation, protecting our atmosphere, and maintaining the delicate balance that allows water to exist in liquid form on our planet's surface. As you drift off to sleep tonight, carried along by the gentle rhythm of these words and the comfort of your bed, remember that you're cradled not just by blankets and pillows, but by invisible forces that have been protecting our world since long before the first star appeared in the night sky. The magnetic field that surrounds our planet is working even now in the darkness, maintaining the shield that has made all life possible. In our next segment, we'll explore how scientists first discovered these invisible forces, the brilliant minds who pieced together the puzzle of Earth's magnetism, and the ingenious experiments that revealed the secrets of our planet's hidden shield. We'll meet the researchers who risked everything to understand the forces that govern our world, and discover how their work laid the foundation for our modern understanding of the magnetic universe that surrounds us. But before we meet those pioneering scientists, let's pause for a moment to consider what it must have been like to live in a world where magnetism was pure magic. For thousands of years, humans witnessed the strange behavior of certain stones that could attract iron, watched compass needles swing toward an invisible north, and had absolutely no framework for understanding what they were experiencing. Imagine the wonder, the mystery, the almost supernatural quality that magnetism must have held for our ancestors. The ancient Greeks knew about magnetic stones, which they called lodestones, and they told stories about shepherds whose iron-tipped staffs would suddenly stick to certain rocks on mountainsides. Chinese scholars wrote about magnetic compasses over 1,000 years ago, describing how these magical needles would always point toward the same direction, as if drawn by an invisible hand. But the idea that our entire planet was itself a giant magnet, wrapped in an invisible field that extended far into space, that notion wouldn't emerge for centuries. The first person to seriously propose that Earth itself was magnetic was a brilliant English physician named William Gilbert, who lived in the late 1500s. Gilbert was Queen Elizabeth's personal doctor, but his true passion lay in understanding the mysterious forces that governed compass needles and lodestones. He spent years conducting careful experiments, mapping the behavior of magnets, and slowly piecing together a revolutionary idea. Gilbert created what he called a terrella, a small spherical lodestone that he polished and shaped to resemble the Earth. When he placed tiny compass needles around this miniature magnetic world, they behaved exactly like compasses on Earth, pointing toward the sphere's magnetic poles. It was an elegant demonstration that our planet must be a massive magnet, and Gilbert's work laid the foundation for centuries of magnetic research to come. But Gilbert's terrella, ingenious as it was, could only explain the compass needle's behavior. The idea that Earth's magnetic field extended far beyond the surface, creating a protective shield in space, wouldn't emerge until the space age brought us face to face with the solar wind and cosmic radiation that our magnetosphere deflects so effortlessly. The true nature of Earth's magnetic field began to reveal itself in the 1950s and 1960s, when the first satellites ventured beyond our atmosphere and started sending back data about the space environment around our planet. Scientists were astonished to discover that Earth's magnetic influence extended thousands of miles into space, creating a vast cavity in the solar wind that they named the magnetosphere. One of the most remarkable discoveries came from studying the way solar particles interact with our magnetic field. The solar wind, that constant stream of charged particles flowing from the sun, doesn't simply bounce off our magnetosphere like rain off an umbrella. Instead, it compresses the field on the day side of Earth, the side facing the sun, while stretching it out into a long tail on the night side, creating a shape that looks remarkably like a comet. This dynamic interaction between the solar wind and our magnetic field creates a complex system of currents and plasma flows that scientists are still working to understand fully. The magnetosphere isn't static, it's constantly responding to changes in the solar wind, flexing and adjusting its shape like a living membrane that breathes with the rhythm of space weather. During periods of high solar activity, when the sun releases particularly energetic bursts of particles, our magnetosphere can become quite disturbed. These magnetic storms can cause the aurora to appear at much lower latitudes than usual, sometimes visible even from regions that normally never see the northern lights, but they can also interfere with satellite communications, disrupt power grids, and create navigation problems for aircraft flying over the poles. The study of these magnetic storms has revealed just how interconnected our planet is with the broader solar system. We're not isolated in space, floating serenely through the void. Instead, we're constantly bathed in the solar wind, our magnetic field acting as both shield and sail, protecting us from harmful radiation, while also channeling some of that solar energy into the beautiful displays of aurora that light up our polar skies. Scientists have discovered that our magnetic field has a memory of sorts recorded in the rocks and sediments that have accumulated over millions of years. By studying the magnetic orientation of ancient lavas and sediments, researchers can reconstruct not just the history of magnetic reversals, but also the intensity and direction of the field at different points in Earth's past. This magnetic memory has revealed some fascinating patterns. For instance, the magnetic field appears to have been much stronger in the past, with some periods showing field strengths nearly double what we experience today. There have also been periods when the field was much weaker, and times when it seemed to fluctuate wildly before settling into a new configuration. One of the most intriguing discoveries is that magnetic reversals don't happen suddenly. Instead, they unfold over thousands of years, with the field gradually weakening, becoming more complex with multiple poles, and then slowly reorganizing itself into its new orientation. During these transition periods, our magnetic shield becomes less effective, though it never disappears entirely. The implications of these magnetic changes for life on Earth have been the subject of intense scientific debate. Some researchers have suggested that periods of weak magnetic field might coincide with evolutionary changes or even mass extinctions as increased cosmic radiation reaches the surface. Others argue that life has proven remarkably resilient to magnetic changes, adapting and evolving regardless of the strength of our planetary shield. What's particularly fascinating is how different regions of our planet experience magnetic changes in different ways. The magnetic poles, for instance, don't stay fixed in one location. The magnetic North Pole has been drifting steadily northward for decades, moving from northern Canada towards Siberia at a rate of about 40 miles per year. This movement is so significant that navigation systems and airport runways have to be regularly updated to account for the changing magnetic declination. The southern magnetic pole wanders as well, though generally more slowly than its northern counterpart. These wandering poles are like restless spirits, never quite settling down, always moving in response to the churning currents of liquid iron deep in the Earth's core. Their movement is one of the most visible signs that our magnetic field is a living, dynamic system. Scientists have also discovered that our magnetic field has quiet periods and active periods, much like the sun has solar cycles. During quiet times, the field remains relatively stable, with only minor fluctuations from day to day. But during active periods, the field can change rapidly, responding to variations in the solar wind and internal changes in the Earth's core. These magnetic variations have practical implications for modern technology. Satellites must be designed to withstand magnetic storms. power grids need protection from induced currents, and navigation systems require constant updates to account for changing magnetic conditions. Our technological civilization has become so dependent on understanding and predicting magnetic behavior that we now have a global network of magnetic observatories monitoring the field around the clock. The beauty of studying Earth's magnetic field is that it connects us to both the deepest parts of our planet and the farthest reaches of space. The field originates in the liquid iron core, nearly 2,000 miles beneath our feet, yet it extends far beyond the Moon's orbit. It's a bridge between the geological processes that shape our planet and the cosmic forces that govern our solar system. As we continue to explore other worlds, we're discovering that magnetic fields are one of the key factors that determine whether a planet can support life as we know it. The presence or absence of a magnetic field can mean the difference between a world with a thick, protective atmosphere and one where the atmosphere has been stripped away by solar wind. Mars provides a sobering example of what can happen when a planet loses its magnetic shield. Billions of years ago, Mars had a substantial magnetic field and likely a much thicker atmosphere. But as the planet's core cooled and its magnetic field weakened, the solar wind began stripping away the atmosphere, leaving behind the thin, cold world we see today. Venus presents another cautionary tale. Despite being similar in size to Earth, Venus has no global magnetic field, and its atmosphere, while thick, is composed primarily of carbon dioxide with surface temperatures hot enough to melt lead. The lack of a magnetic field may have played a role in creating the extreme greenhouse conditions that make Venus so inhospitable to life. These comparisons with other worlds help us appreciate just how remarkable our own magnetic field truly is. It's not just a curiosity or a scientific phenomenon to be studied and understood. It's one of the fundamental reasons why Earth became the vibrant, life-supporting world we call home. The story of Earth's magnetic field is still being written. With each new satellite mission, each deep drilling project, each advance in our understanding of plasma physics and planetary dynamics, we learn more about this invisible shield that has protected us for billions of years. And as we prepare to send humans to other worlds, understanding magnetic fields becomes not just a matter of scientific curiosity, but a crucial element in planning for humanity's future beyond Earth. Tonight, as you settle into sleep, you're surrounded by one of the most remarkable phenomena in the solar system. The magnetic field that cradles our planet is working silently, deflecting harmful radiation, guiding the aurora across polar skies and maintaining the delicate balance that allows life to flourish on this small blue world, spinning through the vast darkness of space. The relationship between Earth's magnetic field and the solar wind creates one of the most dynamic and beautiful interactions in our solar system. When the charged particles streaming from the sun encounter our magnetosphere, they don't simply bounce off like pebbles hitting a wall. Instead, they create a complex dance of energy and matter that reshapes both the solar wind and our magnetic field in ways that scientists are still working to fully understand. Picture the solar wind as a river of charged particles flowing outward from the sun at speeds of hundreds of miles per second. This invisible river carries with it a portion of the sun's own magnetic field, creating what scientists call the interplanetary magnetic field. When this solar magnetic field encounters Earth's magnetosphere, the two fields can either reinforce each other or oppose each other, depending on their relative orientations. When the solar and terrestrial magnetic fields align in the same direction, the interaction is relatively gentle, like two streams of water flowing peacefully alongside each other. But when they point in opposite directions, something remarkable happens. The field lines can reconnect, releasing enormous amounts of energy in a process called magnetic reconnection. This is one of the most powerful phenomena in space physics, capable of accelerating particles to incredible speeds and triggering the magnificent auroral displays that grace our polar skies. The boundary where the solar wind first encounters our magnetosphere is called the bow shock, and it's exactly what it sounds like. Just as a boat moving through water creates a bow wave, Earth's magnetosphere creates a shock wave in the solar wind, deflecting and slowing the incoming particles. This boundary isn't fixed in space. It breathes with the rhythm of solar activity, sometimes extending nearly twice as far from Earth as the Moon's orbit, other times compressed to just a few Earth radii away. Behind the bow shock lies another boundary called the magnetopause, the actual edge of our magnetosphere. This is where Earth's magnetic field becomes strong enough to stand up to the solar wind pressure, creating a cavity in the stream of solar particles. The magnetopause is constantly in motion, rippling and flexing like a flag in the wind as it responds to changes in solar wind pressure and magnetic field orientation. What makes this interaction particularly fascinating is its variability. The Sun isn't a steady, unchanging source of particles and magnetic field. Instead, it's a dynamic star with its own 11-year cycle of activity, punctuated by solar flares, coronal mass ejections, and other explosive events that can dramatically alter the space environment around Earth. During periods of high solar activity, the increased particle flux and stronger magnetic fields can compress our magnetosphere significantly. The bow shock moves closer to Earth, the magnetopause becomes more dynamic, and the entire system becomes more turbulent. These are the times when space weather becomes truly dramatic, with enhanced auroral activity, increased radiation levels, and potential impacts on technological systems. Scientists have discovered that our magnetosphere has a memory of sorts, responding not just to current solar wind conditions, but also to recent history. The system can become loaded with energy during periods of strong solar wind pressure, then release that energy suddenly when conditions change. This loading and unloading process is one of the key mechanisms behind magnetic storms and substorms, the space weather events that can create spectacular auroral displays while also threatening satellites and power grids. The tail of the magnetosphere, that long extension on the night side of Earth, plays a crucial role in this energy storage and release process. During periods of strong solar wind, magnetic field lines on the day side of Earth can be stretched and dragged around to the night side, storing energy like a stretched rubber band. When this energy is suddenly released through magnetic reconnection, it can send particles streaming back toward Earth, creating the substorms that light up the night sky with dancing curtains of aurora. One of the most remarkable discoveries of the space age has been the realization that Earth's magnetosphere isn't an isolated system. Instead, it's connected to a vast network of magnetic fields and charged particles that extends throughout the solar system. The same solar wind that shapes our magnetosphere also interacts with the magnetic fields of other planets, creating a complex web of electromagnetic relationships that scientists are only beginning to understand. Jupiter, with its massive magnetic field generated by metallic hydrogen in its core, creates a magnetosphere so large that it would appear bigger than the full Moon if we could see it from Earth. The interaction between Jupiter's magnetic field and the solar wind creates radio emissions so strong they can be detected by amateur radio operators on Earth. The planet's moons, particularly Io with its volcanic activity, contribute charged particles to this magnetic environment, creating a dynamic system of currents and fields that makes Jupiter's magnetosphere one of the most complex in the solar system. Saturn's magnetosphere, while smaller than Jupiter's, has its own unique characteristics shaped by the planet's spectacular ring system. The ice particles in Saturn's rings interact with the magnetic field, creating phenomena that don't exist anywhere else in the solar system. The planet's moon, Enceladus, with its geysers of water vapor, contributes material to Saturn's magnetosphere, creating a connection between geological activity and magnetic field dynamics that scientists find endlessly fascinating. Even planets without strong magnetic fields create interesting interactions with the solar wind. Mars, despite having lost its global magnetic field billions of years ago, still has localized magnetic anomalies in its crust that create mini magnetospheres. These small pockets of magnetic field can deflect solar wind particles, creating a complex patchwork of protected and unprotected regions on the Martian surface. Venus, with no global magnetic field at all, interacts with the solar wind in a completely different way. The planet's thick atmosphere creates what scientists call an induced magnetosphere, where the solar wind itself generates electrical currents that create a magnetic barrier. It's not as effective as a true planetary magnetic field, but it does provide some protection from the solar wind's effects. The study of these diverse magnetic environments has revealed that magnetic fields are fundamental to the structure and evolution of planetary systems. They're not just passive shields, but active participants in the complex dance of energy and matter that shapes worlds. Understanding how magnetic fields interact with stellar winds, planetary atmospheres, and the charged particle environment of space is crucial for predicting the habitability of exoplanets and planning for future space exploration. As we've sent robotic explorers throughout the solar system, each mission has added new chapters to our understanding of magnetic fields and their role in shaping planetary environments. The Voyager spacecraft, now travelling through interstellar space, have provided unprecedented insights into how our solar system's magnetic environment transitions into the broader galactic medium. The Cassini mission to Saturn revealed the intricate relationships between magnetic fields, ring systems, and moon interactions. More recent missions like Juno at Jupiter and Parker Solar Probe studying the Sun itself continue to expand our knowledge of how magnetic fields operate on scales from planetary to stellar. Back on Earth, our understanding of the magnetosphere has practical implications for everything from satellite design to astronaut safety. The International Space Station orbits within the protective embrace of our magnetosphere, but even there, astronauts experience higher levels of radiation than people on the surface. During major magnetic storms, astronauts may need to take shelter in the most heavily shielded parts of the station to avoid dangerous radiation exposure. The effects of space weather on technology have become increasingly important as our society becomes more dependent on satellite-based systems. GPS navigation, satellite communications, weather forecasting, and many other services we take for granted rely on satellites that operate in the harsh environment of space. Understanding how magnetic storms affect these systems is crucial for maintaining the technological infrastructure that modern civilization depends upon. Ground-based systems aren't immune to the effects of space weather either. When magnetic storms create rapidly changing magnetic fields, they can induce electrical currents in power lines, potentially overloading transformers and causing blackouts. The famous Quebec blackout of 1989 was caused by just such a magnetic storm, leaving millions of people without power for hours. Pipeline systems, which use the Earth's natural electrical currents for corrosion protection, can also be affected by magnetic storms, requiring constant monitoring and adjustment. The aurora, those ethereal displays of light that dance across polar skies, serve as a beautiful reminder of the invisible forces that protect our planet. But they're also a visible manifestation of the energy being deposited in our atmosphere by the interaction between the solar wind and Earth's magnetic field. The colours of the aurora tell a story of atmospheric chemistry, with green light typically coming from oxygen atoms at altitudes around 60 miles, red light from oxygen at higher altitudes, and blue and purple from nitrogen. Indigenous peoples around the world have long recognized the aurora as something special, weaving them into their mythologies and cultural traditions. The Inuit of Alaska and northern Canada have numerous legends about the aurora, often describing them as the spirits of the dead playing games in the sky. Norse mythology spoke of the aurora as reflections from the shields of the Valkyries, the warrior maidens who guided fallen heroes to Valhalla. These cultural connections remind us that humans have always been aware of the magnetic phenomena surrounding our planet, even without understanding their scientific basis. Modern aurora research has revealed that these displays are far more complex than simple curtains of light. High-resolution photography and spectroscopy have shown that auroral displays contain intricate structures, with ribbons, rays, and spirals that change on timescales of seconds. The aurora isn't just a pretty light show, it's a window into the fundamental physics of how charged particles interact with magnetic fields and atmospheric gases. Scientists have discovered that the aurora isn't limited to Earth. Jupiter's moons. Io and Europa create their own auroral displays as they move through the planet's powerful magnetic field. These extraterrestrial auroras provide natural laboratories for studying magnetic field interactions under conditions that don't exist on Earth. The Hubble Space Telescope has captured images of Jupiter's aurora, revealing oval-shaped displays that dwarf anything seen on our planet. The relationship between Earth's magnetic field and climate has been a subject of intense scientific investigation. While the magnetic field doesn't directly control weather patterns, it does influence the amount of cosmic radiation reaching Earth's atmosphere. Some researchers have proposed that changes in magnetic field strength might affect cloud formation by altering the ionization of the atmosphere, though this remains a topic of active debate in the scientific community. What's becoming increasingly clear is that Earth's magnetic field is part of a larger system of electromagnetic interactions that extends from the planet's core to the edge of the solar system. The field lines that emerge from the southern hemisphere and curve through space to re-enter near the North Pole don't simply end there. They're part of a continuous loop that connects the surface of our planet to the far reaches of the magnetosphere, creating a unified electromagnetic environment that responds to changes throughout the entire system. The technology we use to study magnetic fields has evolved dramatically since William Gilbert's simple compass experiments. Today's magnetometers can detect field variations smaller than 1 part in a billion, allowing scientists to map the subtle changes in Earth's magnetic field with unprecedented precision. Satellite constellations like the European Space Agency's SWARM mission continuously monitor the magnetic field from space, providing real-time data about how our planetary shield is changing. Ground-based magnetic observatories, scattered across the globe from Antarctica to the Arctic, work together to create a comprehensive picture of magnetic field variations. These observatories have been operating for decades, some for over a century, creating one of the longest continuous records of any geophysical phenomenon. The data they've collected has revealed patterns and cycles in Earth's magnetic field that would have been impossible to detect from shorter-term observations. The study of paleomagnetism, the record of ancient magnetic fields preserved in rocks and sediments, has opened a window into the deep history of our planet's magnetic field. By analysing the magnetic orientation of volcanic rocks, lake sediments, and even archaeological artefacts like pottery fired in ancient kilns, scientists can reconstruct how Earth's magnetic field has changed over thousands and millions of years. This magnetic detective work has revealed that our planet's field has been remarkably stable for most of its history, with only occasional reversals and gradual changes in intensity. The current weakening of the field, while notable, appears to be within the normal range of variation that has occurred many times in the past. The magnetic field has survived ice ages, asteroid impacts, and massive volcanic eruptions, suggesting that it's a remarkably resilient system. As we prepare for humanity's expansion beyond Earth, understanding magnetic fields becomes crucial for protecting future space travelers. The Moon, with no magnetic field of its own, offers no protection from cosmic radiation and solar particles. Mars, with its weak and patchy magnetic field, provides only limited protection. Future missions to these worlds will need to account for the increased radiation exposure that comes with leaving the protective embrace of Earth's magnetosphere. The search for life beyond Earth has also highlighted the importance of magnetic fields in creating habitable conditions. As we discover more exoplanets orbiting other stars, scientists are beginning to consider whether these distant worlds have magnetic fields that could protect potential life from the harsh radiation environment of space. The presence or absence of a magnetic field may be one of the key factors that determines whether a planet can support life as we know it. Tonight, as you rest in the comfort of your bed, you're surrounded by invisible forces that have been shaping the story of our planet for billions of years. The magnetic field that cradles Earth is more than just a scientific curiosity. It's one of the fundamental reasons why our world became the vibrant, life-supporting haven we call home. From the churning iron in the planet's core to the dancing lights of the aurora, from the protection of our atmosphere to the navigation of migrating birds, Earth's magnetic field weaves through every aspect of our existence, a silent guardian that has made all life possible. The story of how we came to understand Earth's magnetic field is filled with brilliant minds who dared to question the invisible forces around them, often facing ridicule and skepticism from their contemporaries. Long before we had satellites to map the magnetosphere or instruments sensitive enough to detect minute field variations, curious individuals armed with little more than compass needles and careful observation began to unlock the secrets of our planet's magnetic personality. One of the most remarkable figures in this journey was Carl Friedrich Gauss, a German mathematician and physicist whose work in the 1830s laid the mathematical foundation for understanding Earth's magnetic field. Gauss was fascinated by the idea that you could describe something as complex and invisible as magnetism using elegant mathematical equations. He developed what we now call spherical harmonic analysis, a mathematical technique that allows scientists to break down Earth's complex magnetic field into simpler components. What makes Gauss's work particularly impressive is that he achieved this breakthrough using only ground-based measurements from a handful of magnetic observatories scattered across Europe. With no satellites, no global communication networks, and no electronic instruments, he managed to create the first mathematical model of Earth's magnetic field. His equations revealed that the vast majority of our planet's magnetism originates from sources deep within the Earth itself, not from external influences like the sun or moon. Gauss's student, Wilhelm Weber, continued this work and made another crucial discovery. By comparing magnetic measurements taken years apart, Weber noticed that Earth's magnetic field was slowly changing over time. This was a revolutionary insight because it suggested that whatever was generating the magnetic field deep inside our planet was dynamic, constantly in motion. The idea of a living, breathing magnetic field was born from these careful observations of tiny changes measured year after year. The next major leap in understanding came from a British physicist named Lord Kelvin, who in the 1860s proposed that Earth's magnetic field might be generated by electrical currents flowing in the planet's interior. This was a bold suggestion because it required imagining vast rivers of electric current flowing through the Earth's core, something that seemed almost impossible to verify. Yet Kelvin's intuition would prove remarkably prescient, laying the groundwork for our modern understanding of the geodynamo. Around the same time, a French physicist named Gaston Planté was conducting experiments with what he called terrestrial electricity, trying to understand how electrical currents might flow through the Earth itself. Planté's work revealed that our planet was far more electrically active than anyone had imagined, with currents flowing through the ground, the atmosphere, and even the oceans. His discoveries helped establish the connection between electrical and magnetic phenomena that would become central to understanding Earth's magnetic field. The early 20th century brought new tools and new insights to magnetic field research. Scientists began using more sophisticated instruments to measure not just the direction of the magnetic field, but also its strength and the subtle variations that occur over time. These measurements revealed that Earth's magnetic field had a complex structure with regions of stronger and weaker magnetism, and areas where the field lines seemed to twist and turn in unexpected ways. One of the most significant discoveries came from studying the magnetic properties of rocks. In the 1920s, a Japanese scientist named Motonori Matuyama noticed something odd about ancient volcanic rocks. When he measured their magnetic orientation, he found that some rocks seemed to be magnetized in the opposite direction from what you'd expect based on Earth's current magnetic field. This led to the startling realization that our planet's magnetic field must have completely reversed its polarity at some point in the past. The concept of magnetic reversals was initially met with skepticism. The idea that Earth's magnetic north and south poles could swap places seemed almost too dramatic to believe. But as more evidence accumulated from rocks around the world, the reality of magnetic reversals became undeniable. Scientists discovered that these reversals had happened many times throughout Earth's history, roughly every few 100,000 years, though the timing was far from regular. This discovery opened up an entirely new field of research called paleomagnetism, the study of ancient magnetic fields preserved in rocks and sediments. By analysing the magnetic orientation of volcanic lavas, lake sediments, and even archaeological artefacts, scientists could reconstruct the history of Earth's magnetic field going back millions of years. It was like reading a book written in stone, each rock formation holding a chapter of our planet's magnetic story. The development of plate tectonics theory in the 1960s provided another crucial piece of the magnetic puzzle. As scientists mapped the magnetic properties of the ocean floor, they discovered striking patterns of magnetic stripes running parallel to mid-ocean ridges. These stripes represented alternating periods of normal and reversed magnetic polarity, preserved in the volcanic rocks that form the ocean floor. The discovery of these magnetic stripes provided some of the strongest evidence for continental drift and helped establish plate tectonics as the unifying theory of Earth sciences. But perhaps the most revolutionary moment in magnetic field research came with the launch of the first artificial satellites in the 1950s. For the first time, scientists could study Earth's magnetic field from space, free from the interference of ground-based measurements. The early satellite missions revealed that our magnetic field extended far beyond the surface, creating a vast cavity in the solar wind that they named the magnetosphere. The Explorer-1 satellite, launched in 1958, made one of the most surprising discoveries in space science when it detected intense radiation trapped in Earth's magnetic field. These radiation belts, later named the Van Allen belts after their discoverer, James Van Allen, showed that charged particles from space were being captured and held by our magnetic field, creating donut-shaped regions of high-energy radiation around the planet. This discovery completely changed our understanding of the space environment around Earth. Rather than being empty vacuum, the region around our planet was filled with trapped particles, magnetic field lines, and complex electromagnetic phenomena. The magnetosphere wasn't just a passive shield, it was an active, dynamic system that captured, stored, and occasionally released enormous amounts of energy. The 1960s and 1970s saw an explosion of satellite missions dedicated to studying Earth's magnetic environment. The OGO series of satellites, the IMP missions, and many others began to map the three-dimensional structure of the magnetosphere in unprecedented detail. These missions revealed that our magnetic field was constantly changing, responding to variations in the solar wind like a flag fluttering in a cosmic breeze. One of the most important discoveries came from studying how the solar wind interacts with Earth's magnetic field. Scientists found that when the solar wind's magnetic field aligned with Earth's field, the interaction was relatively calm. But when the two fields pointed in opposite directions, they could reconnect explosively, releasing enormous amounts of energy and triggering magnetic storms that could disrupt power grids and communications systems on Earth. The study of magnetic reconnection became one of the most active areas of space physics research. This process, where magnetic field lines break and reconnect, releasing stored energy almost instantaneously, occurs not just around Earth but throughout the solar system and beyond. Understanding magnetic reconnection has implications for everything from solar flares to the behavior of plasma in fusion reactors. As computer technology advanced, scientists began creating increasingly sophisticated models of Earth's magnetic field and its interaction with the solar wind. These models, running on powerful supercomputers, could simulate the complex dance of charged particles and magnetic fields that occurs in the magnetosphere. By comparing these simulations with satellite observations, researchers could test their theories about how magnetic fields behave under different conditions. The development of global positioning systems in the 1980s and 1990s brought magnetic field research into the realm of practical applications. GPS satellites orbiting high above Earth's surface are constantly buffeted by space weather events that can affect their accuracy. Understanding how magnetic storms and other space weather phenomena impact satellite operations became crucial for maintaining the reliability of navigation systems that millions of people depend on every day. Modern magnetic field research has become increasingly international and collaborative. The International Geomagnetic Reference Field, updated every 5 years, represents the combined efforts of magnetic observatories and research institutions around the world. This global collaboration has created the most accurate and comprehensive model of Earth's magnetic field ever developed, allowing scientists to track changes with unprecedented precision. The European Space Agency's SWARM mission, launched in 2013, represents the current state-of-the-art in magnetic field measurement. This constellation of 3 satellites continuously monitors Earth's magnetic field from space, providing real-time data about how our planetary shield is changing. The mission has already revealed new insights about the structure of the magnetic field and the processes that generate it deep within Earth's core. One of the most intriguing recent discoveries is that Earth's magnetic field is changing more rapidly than previously thought. The magnetic North Pole is drifting from northern Canada towards Siberia at an accelerating rate, moving about 40 miles per year. This rapid movement has forced scientists to update navigation systems and magnetic declination charts more frequently than ever before. The South Atlantic anomaly, a region where Earth's magnetic field is particularly weak, has also been growing and changing in ways that concern scientists. This area, centered over the South Atlantic Ocean, allows more cosmic radiation to reach Earth's atmosphere and can cause problems for satellites passing through it. Understanding why this anomaly exists and how it's evolving is one of the current frontiers of magnetic field research. Climate scientists have also become interested in Earth's magnetic field because of its potential influence on atmospheric processes. While the magnetic field doesn't directly control weather patterns, it does affect the amount of cosmic radiation reaching Earth's atmosphere. Some researchers have proposed that changes in magnetic field strength might influence cloud formation and atmospheric chemistry, though this remains a topic of active debate. The search for life beyond Earth has highlighted the importance of magnetic fields in creating habitable conditions. As we discover more exoplanets orbiting other stars, scientists are beginning to consider whether these distant worlds have magnetic fields that could protect potential life from stellar radiation. The presence or absence of a magnetic field may be one of the key factors that determines whether a planet can support life as we know it. Recent missions to Mars have provided fascinating insights into what happens when a planet loses its magnetic field. The MAVEN spacecraft, which has been studying Mars' atmosphere since 2014, has shown that the solar wind is still stripping away the Martian atmosphere at a rate of about 100 grams per second. This ongoing atmospheric loss helps explain how Mars transformed from a potentially habitable world with a thick atmosphere to the cold, dry planet we see today. The study of magnetic fields has also become important for understanding space weather and its effects on technology. As our society becomes increasingly dependent on satellite-based systems, understanding how magnetic storms affect these systems is crucial for maintaining the technological infrastructure that modern civilization depends upon. Space weather forecasting has become as important as terrestrial weather forecasting for many industries. One of the most exciting frontiers in magnetic field research is the study of magnetic reconnection in laboratory settings. Scientists have built specialized devices that can recreate the conditions where magnetic field lines break and reconnect, allowing them to study this fundamental process under controlled conditions. These laboratory experiments are helping to improve our understanding of how magnetic reconnection works in space and how it might be harnessed for practical applications like fusion energy. The development of quantum sensors has opened new possibilities for magnetic field measurement. These incredibly sensitive devices can detect magnetic field variations smaller than anything previously possible, allowing scientists to map the subtle changes in Earth's magnetic field with unprecedented precision. Quantum magnetometers are already being used to study everything from mineral deposits to archaeological sites, and their applications continue to expand. As we look toward the future, magnetic field research continues to evolve and expand. New satellite missions are being planned to study not just Earth's magnetic field, but also the magnetic environments of other planets. The proposed interstellar probe mission would venture beyond the edge of the solar system to study how our local magnetic environment transitions into the broader galactic medium. The story of magnetic field research is a testament to human curiosity and ingenuity. From ancient observations of lodestones to modern satellite missions, each generation of scientists has built upon the work of their predecessors, gradually unveiling the secrets of the invisible forces that surround our planet. The magnetic field that protects Earth is no longer a mystery but a well-understood phenomenon, yet it continues to surprise and delight researchers with its complexity and beauty. Tonight, as you settle into the comfort of your bed, you're surrounded by the legacy of centuries of scientific discovery. The magnetic field that cradles our planet has been studied, measured, and modelled by countless researchers who dedicated their lives to understanding the invisible forces that make life possible. Their work has revealed that we live in a universe far more interconnected and dynamic than our ancestors could have imagined, where magnetic fields link planets to stars and create the conditions necessary for life to flourish. The journey from Gilbert's simple terrella to modern satellite constellations represents one of the greatest achievements in human understanding. We've learned to read the magnetic language of rocks, to predict space weather, and to appreciate the delicate balance that keeps our world habitable. The magnetic field that once seemed like pure magic has become a trusted companion, a protective shield that we can study, understand, and even predict. As you drift off to sleep, carried by the gentle rhythm of these words, remember that you're part of a story that began billions of years ago when our planet first developed its magnetic personality. The same forces that guide compass needles and create the aurora are working even now in the darkness, maintaining the invisible shield that has made all life possible. In the morning, when you wake to a world protected by forces you cannot see, you'll be participating in the ongoing miracle of existence on a magnetically shielded planet, spinning through space in the embrace of invisible fields that have kept us safe since the very beginning of time. The practical implications of understanding Earth's magnetic field extend far beyond academic curiosity into the very fabric of our daily lives. Every time you use your smartphone's GPS navigation, check the weather forecast from satellite data, or even use a simple compass for hiking, you're relying on our collective understanding of how magnetic fields behave and change over time. Modern aviation depends heavily on magnetic navigation systems, particularly for flights over the polar regions where GPS signals can be unreliable. Pilots flying routes across the Arctic must constantly adjust their instruments to account for the wandering magnetic North Pole and the complex magnetic field variations that occur near the poles. The Federal Aviation Administration updates magnetic declination charts regularly, ensuring that aircraft navigation systems remain accurate as our planet's magnetic field continues its slow dance of change. The shipping industry too relies on magnetic navigation for vessels crossing vast oceans, where other navigation aids are unavailable. Modern ships carry sophisticated magnetometers that can detect nearby submarines or underwater obstacles by measuring disturbances in the local magnetic field. These same principles are used in marine archaeology, where researchers use magnetic surveys to locate shipwrecks and ancient harbours buried beneath the sea floor. Perhaps most remarkably, the study of magnetic fields has revolutionized our understanding of life itself. Scientists have discovered that many animals possess an almost supernatural ability to sense Earth's magnetic field, using it as an invisible highway system for navigation across vast distances. Sea turtles can navigate across entire ocean basins, returning to the exact beaches where they were born decades earlier, guided by their innate ability to read the planet's magnetic signature. Migratory birds perform even more remarkable feats of magnetic navigation. Arctic terns migrate from Arctic to Antarctic and back again each year, covering roughly 44,000 miles in their annual journey. Recent research has revealed that these birds can sense not just the direction of magnetic field lines, but also their intensity and inclination, creating a three-dimensional magnetic map that guides them across hemispheres with astonishing precision. The mechanism behind this biological magnetism remained a mystery for decades until scientists discovered that many animals have tiny crystals of magnetite embedded in specialized cells. These microscopic compass needles, often found in the beaks of birds or the noses of mammals, can detect magnetic field variations smaller than what our most sensitive instruments could measure until recently. It's as if evolution has equipped these creatures with quantum sensors millions of years before humans invented such technology. Even more intriguing is the discovery that some animals may use quantum mechanics to sense magnetic fields. Certain birds appear to have proteins in their eyes that can detect magnetic fields through quantum entanglement, allowing them to literally see the magnetic field as patterns of light and shadow overlaid on their visual field. This quantum compass gives them a magnetic sense that's integrated with their vision, creating a form of perception that humans can barely imagine. Bacteria, those ancient and resilient life forms, have their own relationship with magnetism. Magnetotactic bacteria contain chains of magnetite crystals that act like tiny compass needles, helping them navigate through sediments and water columns toward optimal living conditions. These microscopic organisms have been using magnetic navigation for billions of years, long before complex life forms evolved their more sophisticated magnetic sensing abilities. The discovery of biological magnetism has opened entirely new fields of research and potential applications. Scientists are studying how disruptions to Earth's magnetic field might affect animal navigation and migration patterns. There's growing concern that the rapid movement of the magnetic poles and the weakening of the field in some regions could be contributing to the navigation problems observed in some migratory species. Climate change adds another layer of complexity to these magnetic navigation systems. As ocean temperatures and current patterns shift, the magnetic signatures that marine animals use for navigation may be changing in ways that confuse their ancient guidance systems. Whales and dolphins, which are thought to use magnetic navigation for their long-distance migrations, have shown unusual beaching behaviors in some regions where magnetic anomalies occur. The relationship between magnetic fields and human health has also become a subject of intense scientific interest. While humans don't appear to have the strong magnetic sensing abilities of migratory animals, some researchers have found evidence that we may retain vestigial magnetic sensitivity. Studies have suggested that people can sometimes sense direction better than random chance would predict, though this ability varies greatly among individuals and remains poorly understood. The growing field of biomagnetism explores how magnetic fields affect biological processes. Every electrical current in the body, from the firing of neurons to the beating of the heart, creates tiny magnetic fields that can be detected by sensitive instruments. Magnetoencephalography uses these biological magnetic fields to study brain activity with remarkable precision, offering new insights into how our minds work and how various neurological conditions affect brain function. Some researchers have proposed that Earth's magnetic field variations might influence biological rhythms and even evolution over long timescales. During periods when the magnetic field is weak or undergoing reversals, increased cosmic radiation reaches Earth's surface, potentially affecting mutation rates and evolutionary processes. While this remains a topic of active debate, it raises fascinating questions about the relationship between planetary magnetic fields and the development of life. The technological revolution of the past few decades has made us increasingly dependent on systems that are vulnerable to magnetic field variations. The Global Positioning System, which now guides everything from smartphone maps to precision agriculture, relies on atomic clocks aboard satellites that can be affected by space weather events. During major magnetic storms, GPS accuracy can degrade significantly, causing problems for systems that depend on precise positioning. Power grids represent another vulnerable point in our technological infrastructure. When magnetic storms create rapidly changing magnetic fields, they can induce electrical currents in power lines, potentially overloading transformers and causing widespread blackouts. The Great Magnetic Storm of 1989 caused a 9-hour blackout in Quebec, leaving 6 million people without power and causing hundreds of millions of dollars in damage. The increasing sophistication of our technology has, paradoxically, made us more vulnerable to space weather events. Modern electronics are often more sensitive to electromagnetic interference than older, simpler devices. Satellites, with their delicate circuits exposed to the harsh environment of space, are particularly vulnerable to the effects of magnetic storms and solar particle events. Financial markets, too, can be affected by space weather. High-frequency trading systems that depend on precise timing can be disrupted by GPS anomalies caused by magnetic storms. Communications satellites that carry financial data can be damaged or disrupted by space weather events, potentially affecting global markets in ways that are only beginning to be understood. The study of magnetic fields has also revealed the interconnected nature of our planet's systems. The magnetic field doesn't exist in isolation, but interacts with the atmosphere, the oceans, and even the solid Earth in complex ways. Changes in the magnetic field can affect atmospheric chemistry, particularly in the upper atmosphere, where charged particles interact with gases to create phenomena like the aurora. Ocean currents, those vast rivers of seawater that transport heat around the globe, create their own magnetic signatures as the conductive seawater moves through Earth's magnetic field. Scientists can use these magnetic signals to study ocean circulation patterns and monitor changes in current strength and direction. This magnetic oceanography provides a new tool for understanding how ocean currents might change in response to climate change. The solid Earth itself responds to magnetic field variations through a process called electromagnetic induction. When the magnetic field changes, it induces electrical currents in the conductive layers of the Earth's interior. These currents, in turn, create their own magnetic fields that interact with the original field changes. Understanding these induction effects is crucial for accurately modeling how the magnetic field behaves and predicts how it might change in the future. Volcanic activity has a complex relationship with magnetic fields. As magma rises through the Earth's crust, it can disturb local magnetic field patterns, providing early warning signs of potential eruptions. The iron-rich minerals in volcanic rocks record the magnetic field orientation at the time of cooling, creating a permanent record of past volcanic activity and magnetic field changes. Earthquake research has also benefited from magnetic field studies. Some scientists have reported magnetic field anomalies before major earthquakes, though the mechanism behind these changes remains poorly understood. The stress buildup that precedes earthquakes might affect the magnetic properties of rocks, creating detectable changes in the local magnetic field. The mining industry uses magnetic surveys to locate ore deposits and understand subsurface geology. Different minerals have different magnetic properties, creating signatures that can be detected from aircraft or satellites. These magnetic maps help geologists understand the structure of the Earth's crust and locate valuable mineral resources without the need for expensive drilling programs. Archaeological applications of magnetic field research have revealed hidden treasures and ancient settlements. Buried structures, pottery kilns, and even ancient hearths create magnetic anomalies that can be detected centuries or millennia after they were abandoned. Magnetic surveys have revealed entire Roman cities, medieval settlements, and prehistoric sites that show no surface evidence of their existence. Environmental monitoring increasingly relies on magnetic field measurements to track pollution and contamination. Heavy metals and other pollutants can alter the magnetic properties of soils and sediments, creating signatures that can be detected and mapped. This magnetic environmental monitoring provides a cost-effective way to assess contamination over large areas. The future of magnetic field research promises even more exciting discoveries and applications. Quantum sensors are becoming increasingly sophisticated, offering the possibility of detecting magnetic field variations smaller than anything currently possible. These ultra-sensitive instruments could reveal new details about how Earth's magnetic field is generated and how it interacts with other planetary systems. Space exploration missions are increasingly incorporating magnetic field studies into their scientific objectives. The European Space Agency's Bepi-Colombo mission to Mercury will study that planet's magnetic field in unprecedented detail, helping scientists understand how magnetic fields are generated in different planetary environments. Future missions to the outer planets will explore the exotic magnetic environments of gas giants and their moons. The search for extraterrestrial life has highlighted the importance of magnetic fields in creating habitable conditions. As we discover more exoplanets orbiting other stars, scientists are developing techniques to detect the magnetic fields of these distant worlds. The presence of a strong magnetic field could be one of the key signatures that indicates a planet might be capable of supporting life as we know it. Fusion energy research has found unexpected connections to magnetic field studies. The same plasma physics that governs the behavior of charged particles in Earth's magnetosphere also applies to the confined plasmas in fusion reactors. Understanding magnetic reconnection and plasma instabilities in space helps inform the design of more efficient fusion energy systems. Climate modelling has begun to incorporate magnetic field effects more seriously as scientists recognise the complex interactions between space weather, atmospheric chemistry, and climate systems. While the magnetic field doesn't directly control Earth's climate, it does influence the amount of cosmic radiation reaching the atmosphere and the chemical processes that occur in the upper atmosphere. The development of magnetic shielding technology for space exploration draws directly from our understanding of how Earth's natural magnetic field protects us. Future missions to Mars and other worlds without strong magnetic fields will need artificial magnetic shields to protect astronauts from the harsh radiation environment of space. Magnetic levitation technology, already used in some high-speed trains, could revolutionize transportation if scaled up effectively. Understanding how magnetic fields interact with conductive materials has led to the development of more efficient magnetic bearings, contactless power transfer systems, and even magnetic refrigeration technologies. The study of Earth's magnetic field has revealed that we live in a universe where invisible forces shape the destiny of worlds. From the churning iron in planetary cores to the vast magnetic fields that thread through galaxies, magnetism is one of the fundamental forces that organizes matter and energy on every scale, from atoms to galaxy clusters. Tonight, as you rest peacefully in your bed, you're surrounded by the culmination of centuries of human curiosity and scientific discovery. The magnetic field that protects our planet is no longer a mystery, but a well-understood phenomenon that continues to reveal new secrets about the nature of our world. Every compass needle that points north, every migrating bird that finds its way across continents, every aurora that dances across polar skies is a reminder of the invisible forces that make life on Earth possible. The story of magnetic field research is far from over. Each new discovery opens new questions, each technological advance reveals new applications, and each generation of scientists builds upon the work of their predecessors to deepen our understanding of the magnetic universe we inhabit. As you drift towards sleep, carried by the gentle rhythm of these words, remember that you're part of an ongoing adventure of discovery, a quest to understand the invisible forces that connect us to the cosmos and make our existence possible in this vast, magnificent, magnetically protected corner of the universe. The beauty of Earth's magnetic field lies not just in its protective qualities, but in its remarkable ability to respond and adapt to the ever-changing conditions of our solar neighborhood. Like a skilled conductor leading an orchestra, our magnetosphere orchestrates a complex symphony of interactions between charged particles, electromagnetic fields, and atmospheric processes that creates one of the most dynamic environments in the solar system. When we think about protection, we often imagine something static and unchanging, like a sturdy umbrella or a solid wall. But Earth's magnetic shield is nothing like that. It breathes, it flexes, it responds to every subtle change in the solar wind with an elegance that would make the most accomplished dancer envious. During quiet periods, when the sun is relatively calm, our magnetosphere extends gracefully into space, its boundaries well defined and stable. But when solar activity increases, when our star releases energetic bursts of particles and magnetic fields, our protective shield responds like a living thing. The magnetosphere compresses on the side facing the sun, its boundaries pushed inward by the increased pressure of the solar wind. At the same time, the field lines on the night side of Earth stretch out into a long tail that can extend beyond the orbit of the Moon. This isn't a sign of weakness, it's a demonstration of the incredible adaptability that has allowed our magnetic field to protect Earth for billions of years through every type of space weather imaginable. Scientists have discovered that our magnetosphere has what they call substorms, sudden releases of energy that can light up the aurora and send particles cascading back toward Earth. These substorms aren't random events, they're part of a carefully orchestrated process of energy storage and release that helps our magnetic field manage the constant input of solar energy. When the solar wind pressure builds up, the magnetosphere stores that energy in its stretched field lines like a rubber band being pulled taut. When the energy is finally released, it creates some of the most spectacular light shows on Earth. The aurora that results from these magnetic substorms is more than just a beautiful display. It's a visible manifestation of our planet's ability to transform potentially harmful solar energy into harmless light. The charged particles that could damage our atmosphere or interfere with our technology are instead guided along magnetic field lines to the polar regions, where they create gentle collisions with atmospheric gases that produce those ethereal curtains of green, blue, and red light. What makes this process even more remarkable is its efficiency. Our magnetosphere doesn't just randomly deflect solar particles, it sorts them, channels them, and directs them to where they can do the least harm and create the most beauty. The most energetic particles are trapped in the Van Allen radiation belts, held safely away from Earth's surface by the magnetic field's invisible embrace. Less energetic particles are guided to the polar regions where they create the aurora, and the vast majority of solar wind particles are simply deflected around our magnetic bubble, flowing past Earth like water around a stone in a stream. This sophisticated system of particle management has been operating for billions of years, long before life appeared on Earth's surface. The magnetic field didn't evolve to protect us specifically, yet it has done so with remarkable effectiveness. It's as if our planet developed its own immune system, a way of dealing with the constant bombardment of particles and radiation from space that could otherwise sterilize the surface and strip away our atmosphere. The relationship between Earth's magnetic field and our atmosphere is particularly intimate and complex. The field doesn't just protect our atmosphere from being stripped away by the solar wind, it actively participates in atmospheric processes. High in the ionosphere, where the atmosphere meets space, charged particles trapped by the magnetic field interact with atmospheric gases to create a complex soup of ions and electrons. This ionospheric plasma plays a crucial role in radio communications, reflecting certain radio frequencies back to Earth and allowing long-distance communication that would otherwise be impossible. The same magnetic processes that create the aurora also influence how radio waves propagate through the atmosphere, affecting everything from AM radio reception to satellite communications. The magnetic field also influences atmospheric chemistry in subtle but important ways. Cosmic rays, those high-energy particles from deep space, are partially deflected by our magnetic shield. The ones that do get through can trigger chemical reactions in the upper atmosphere, contributing to the formation of certain atmospheric gases. Some scientists have even proposed that changes in magnetic field strength over geological time might have influenced the evolution of Earth's atmosphere and climate. But perhaps the most fascinating aspect of our magnetic field is how it connects Earth to the broader electromagnetic environment of the solar system. Our magnetosphere doesn't exist in isolation. It's part of a vast network of magnetic fields and charged particle flows that extends throughout our cosmic neighborhood. The same solar wind that shapes our magnetosphere also interacts with the magnetic fields of other planets, creating a complex web of electromagnetic relationships. Jupiter's massive magnetosphere, powered by the planet's rapid rotation and metallic hydrogen core, creates radio emissions so strong they can interfere with radio telescopes on Earth. The interaction between Jupiter's magnetic field and its moon Io's volcanic activity creates electrical currents more powerful than anything on Earth. Saturn's magnetosphere interacts with its ring system in ways that create phenomena unique in the solar system. Even planets without strong magnetic fields participate in this electromagnetic dance. Mars, despite having lost its global magnetic field billions of years ago, still has localized magnetic anomalies that create mini magnetospheres. These small pockets of magnetic protection interact with the solar wind in complex ways, creating a patchwork of protected and exposed regions on the Martian surface. Venus, with no global magnetic field at all, demonstrates what happens when a planet faces the solar wind without magnetic protection. The planet's thick atmosphere creates an induced magnetosphere, where the solar wind itself generates electrical currents that provide some protection. But this induced field is far less effective than a true planetary magnetic field, and Venus has likely lost much of its original atmosphere to space over geological time. These comparisons with other worlds help us appreciate just how remarkable our own magnetic field truly is. Earth sits in a kind of electromagnetic sweet spot, with a magnetic field strong enough to provide excellent protection, but not so strong that it creates the intense radiation environments found around gas giants like Jupiter. Our field is stable enough to provide consistent protection over geological time, yet dynamic enough to respond effectively to changes in space weather. The study of how magnetic fields interact with stellar winds has become increasingly important as we search for potentially habitable exoplanets. Scientists are now developing techniques to detect the magnetic fields of planets orbiting other stars, using the radio emissions and other signatures that result from the interaction between planetary magnetic fields and stellar winds. The presence of a strong magnetic field could be one of the key indicators that a distant planet might be capable of supporting life. This connection between magnetism and habitability extends beyond just protection from stellar radiation. Magnetic fields may also play a role in maintaining the atmospheric pressure and composition necessary for liquid water to exist on a planet's surface. Without magnetic protection, even a planet in the habitable zone around its star might gradually lose its atmosphere and become uninhabitable. The search for magnetic signatures from exoplanets has led to some of the most sensitive radio astronomy ever attempted. Scientists are looking for extremely weak radio signals that might indicate the presence of auroral activity on distant worlds. Finding such signals would not only confirm the presence of a magnetic field, but also suggest that the planet has an atmosphere dense enough to support auroral displays. Back on Earth, our understanding of magnetic field dynamics continues to evolve as new technologies allow us to probe deeper into the mysteries of our planetary shield. Modern satellite constellations can map the three-dimensional structure of our magnetosphere in real time, revealing details about how energy flows through the system and how different regions of the magnetosphere communicate with each other. One of the most surprising recent discoveries is that our magnetosphere has a kind of memory, retaining information about past solar wind conditions and releasing that stored energy hours or even days later. This magnetic memory effect helps explain why space weather events can sometimes occur even when the solar wind appears calm, as stored energy from previous solar activity is suddenly released. The magnetic field lines that thread through our magnetosphere aren't static structures, but dynamic pathways that can reconnect, merge, and separate in response to changing conditions. This process of magnetic reconnection, where field lines break and rejoin, is one of the most efficient mechanisms in the universe for converting magnetic energy into kinetic energy. Understanding magnetic reconnection has implications far beyond Earth's magnetosphere, as this process occurs in solar flares, stellar corona, and even in the magnetic fields that thread through galaxies. The complexity of magnetic reconnection in Earth's magnetosphere provides a natural laboratory for studying this fundamental plasma physics process. Scientists can observe reconnection events in real time using satellite data, then test their theories about how this process works under different conditions. These studies are helping to improve our understanding of fusion energy, where controlled magnetic reconnection might be used to maintain the high temperatures necessary for nuclear fusion. The relationship between magnetic fields and the flow of energy through plasma has also found applications in space propulsion. Ion drives and plasma thrusters, already used on some spacecraft, rely on magnetic fields to accelerate charged particles and create thrust. Future spacecraft might use magnetic sails, large loops of superconducting wire that interact with planetary magnetic fields to provide propulsion without the need for chemical fuel. The study of Earth's magnetic field has also revealed the importance of magnetic shielding for future space exploration. As humans venture beyond the protective embrace of our magnetosphere, they'll be exposed to radiation levels that could be dangerous over long periods. Understanding how natural magnetic fields provide protection is informing the design of artificial magnetic shields that might protect spacecraft and space habitats. Some proposed missions to Mars include the idea of creating an artificial magnetic field to protect the planet's remaining atmosphere from further erosion by the solar wind. Such a magnetic shield, positioned at the point between Mars and the Sun, where gravitational forces balance, could potentially help restore some of Mars' atmospheric density over geological timescales. The technological challenges of creating artificial magnetic fields strong enough to deflect the solar wind are enormous, but they're not insurmountable. Superconducting magnets, already used in medical imaging and particle accelerators, could potentially be scaled up to create spacecraft magnetic shields. The same principles that govern Earth's natural magnetic field could be applied to protect human settlements on worlds without magnetic protection. Climate scientists have also begun to appreciate the subtle but important ways that magnetic field variations can influence Earth's climate system. While the magnetic field doesn't directly control weather patterns, it does affect the amount of cosmic radiation reaching the atmosphere and the chemical processes that occur in the upper atmosphere. These high-altitude effects can cascade down through the atmosphere, potentially influencing cloud formation and atmospheric circulation patterns. The relationship between magnetic field strength and cosmic ray flux has led some researchers to investigate whether magnetic field variations might have contributed to past climate changes. During periods when Earth's magnetic field was weak, increased cosmic radiation might have affected atmospheric chemistry in ways that influenced global climate. While this remains a topic of active research and debate, it highlights the interconnected nature of Earth's various systems. Space weather forecasting has become increasingly important as our technological civilization becomes more dependent on satellite-based systems. Just as meteorologists predict terrestrial weather to help people plan their activities, space weather forecasters monitor solar activity and magnetic field conditions to predict when space weather events might affect technology. The economic impact of space weather has grown significantly in recent decades. A major magnetic storm could potentially cause billions of dollars in damage to satellite systems, power grids, and other technological infrastructure. Airlines reroute polar flights during major magnetic storms to avoid communication blackouts and increased radiation exposure. Even oil pipelines, which use electrical systems for corrosion protection, can be affected by the induced currents that magnetic storms create in the ground. The insurance industry has begun to take space weather seriously, developing policies to cover losses from magnetic storms and solar particle events. The growing awareness of space weather risks has led to increased investment in space weather monitoring and prediction systems, as well as the development of more resilient technologies that can better withstand electromagnetic disturbances. educational institutions around the world have begun incorporating space weather and magnetic field studies into their curricula, recognizing that future generations will need to understand these phenomena as our technological dependence continues to grow. Students are learning to monitor real-time space weather data, analyze magnetic field measurements, and understand how space weather affects the technology they use every day. The democratization of space weather monitoring through internet-connected instruments has allowed amateur scientists and students to participate in magnetic field research. Small magnetometers, once accessible only to major research institutions, can now be built by high school students and connected to global networks that monitor Earth's magnetic field around the clock. This citizen science approach to magnetic field monitoring has already led to new discoveries about how magnetic disturbances propagate around the globe. The dense network of amateur magnetic observatories provides spatial resolution that would be impossible to achieve with professional instruments alone, revealing fine-scale details about how magnetic waves travel through Earth's crust and atmosphere. The artistic and cultural impact of magnetic field research has been just as significant as its scientific contributions. The invisible beauty of magnetic field lines has inspired artists, musicians, and writers to create works that help people visualize and understand these hidden forces. Magnetic field visualizations have become a new form of scientific art, revealing the elegant mathematical structures that govern the space around our planet. Musicians have composed pieces inspired by the rhythms and harmonics of magnetic field oscillations, translating the electromagnetic music of our magnetosphere into sounds that human ears can appreciate. The frequency patterns of magnetic field waves, when converted to audio, create haunting melodies that seem to capture the alien beauty of space weather phenomena. Writers and filmmakers have drawn inspiration from the protective nature of Earth's magnetic field, using it as a metaphor for the invisible forces that shape our lives and protect us from dangers we cannot see. The magnetic field has become a symbol of Earth's resilience and the delicate balance that maintains habitability on our planet. The philosophical implications of magnetic field research have also captured the imagination of thinkers and dreamers. The realization that we live within an invisible protective bubble has changed how many people think about Earth's place in the cosmos. We're not just passengers on a rock floating through space, we're inhabitants of a carefully shielded world that has been protecting life for billions of years. This protective aspect of Earth's magnetic field has led to new perspectives on environmental stewardship and planetary protection. Just as we've learned to appreciate the importance of Earth's atmosphere and biosphere, we're beginning to understand the crucial role that magnetic fields play in maintaining planetary habitability. Some researchers have proposed that magnetic field strength should be considered alongside other environmental indicators when assessing the health of our planet. The study of magnetic fields has also revealed the deep connections between Earth's interior and its space environment. The magnetic field that protects us from space weather is generated by the same geological processes that drive plate tectonics, create earthquakes, and shape the surface of our planet. The liquid iron core that generates our magnetic field is also responsible for the heat that drives volcanic activity and continental drift. This connection between the deep Earth and space means that changes in our planet's interior can affect the space weather environment around Earth. Variations in core dynamics that alter the magnetic field can change how our magnetosphere responds to solar wind variations, creating feedback loops between geological and space weather processes that scientists are only beginning to understand. The long-term evolution of Earth's magnetic field is intimately connected to the cooling history of our planet. As Earth's interior gradually cools over geological time, the processes that generate the magnetic field may eventually weaken or cease altogether. Understanding this long-term evolution is crucial for predicting how our magnetic protection might change over millions or billions of years. Some models suggest that Earth's magnetic field might weaken significantly over the next billion years as the planet's interior continues to cool. This gradual weakening could eventually leave our planet more vulnerable to solar wind erosion, though the timescales involved are so vast that they dwarf human civilization by factors of millions. The study of magnetic field evolution on other planets provides clues about Earth's magnetic future. Mars likely had a strong magnetic field early in its history, but lost it as the planet's interior cooled and core convection ceased. Understanding why Mars lost its magnetic field while Earth retained its protection helps scientists predict how long our own magnetic shield might last. Venus presents a different puzzle, as the planet is similar in size to Earth but has no global magnetic field despite having a presumably molten core. The reasons for Venus's lack of magnetic protection remain mysterious, but they may be related to the planet's extremely slow rotation or its different thermal evolution history. Tonight, as you rest comfortably in your bed, you're surrounded by invisible forces that connect the deepest parts of our planet to the farthest reaches of space. The magnetic field that cradles Earth is more than just a protective shield. It's a bridge between worlds, a connection between the geological processes that shape our planet's surface and the cosmic forces that govern our solar system. From the churning iron currents in Earth's core to the dancing lights of the aurora, from the migration paths of sea turtles to the navigation systems that guide our spacecraft, magnetic fields weave through every aspect of existence on our planet. They remind us that we live in a universe where invisible forces can be more powerful than anything we can see, where protection and beauty can emerge from the same fundamental processes, and where the story of our planet is written in languages of magnetism that we're only now learning to read. As you drift towards sleep, carried by the gentle rhythm of these words, and the comfort of knowing that you're protected by forces far greater than yourself. Remember that every breath you take, every dream you dream, every moment of peace you find is made possible by the invisible embrace of Earth's magnetic field. In the darkness of space, our planet shines not just with reflected sunlight, but with the invisible glow of magnetic protection, a beacon of habitability in the vast cosmic ocean that surrounds us all. The future of our relationship with Earth's magnetic field promises to be as dynamic and fascinating as the field itself. As we stand on the threshold of becoming a truly spacefaring civilization, our understanding of magnetic protection becomes not just academically interesting, but practically essential for human survival beyond our home planet. Consider the challenges facing the first human settlers on Mars. Without the protective embrace of a global magnetic field, these brave pioneers will be exposed to radiation levels that could prove dangerous over extended periods. The thin Martian atmosphere provides little shielding from cosmic rays and solar particles, meaning that future Mars colonies will need to develop innovative solutions for magnetic protection. Some researchers have proposed creating localized magnetic fields around Martian settlements, using superconducting coils to generate protective bubbles that could deflect harmful radiation. These artificial magnetospheres would need to be far smaller than Earth's natural field, but could still provide crucial protection for human habitats. The engineering challenges are formidable, but they're not insurmountable with advancing superconductor technology and our growing understanding of how magnetic fields interact with charged particles. The asteroid mining operations that may become reality in the coming decades will face similar challenges. Spacecraft operating in the asteroid belt, far from any planetary magnetic protection, will need robust shielding systems to protect both human crews and sensitive electronics from the constant bombardment of cosmic radiation. Understanding how Earth's magnetic field provides such elegant protection is informing the design of these future shielding systems. Even closer to home, the growing population of satellites in Earth orbit faces increasing challenges from space weather events. As magnetic storms become more intense due to the solar maximum phases of our star's 11-year cycle, satellite operators must constantly balance the benefits of higher orbits against the increased radiation exposure that comes with venturing beyond the protective inner regions of our magnetosphere. The commercial space industry has begun incorporating space weather forecasting into their operational planning, recognizing that a major magnetic storm could disable entire satellite constellations worth billions of dollars. The same invisible forces that create beautiful auroral displays can also wreak havoc on the delicate electronics that power our modern communication and navigation systems. Climate researchers continue to explore the subtle connections between magnetic field variations and Earth's atmospheric systems. While the magnetic field doesn't directly control weather patterns, new research suggests that changes in cosmic ray flux caused by magnetic field variations might influence cloud formation processes in ways that could affect regional climate patterns. These atmospheric connections highlight the interconnected nature of Earth's systems, where changes in the deep interior that affect magnetic field generation can cascade upward through the atmosphere and potentially influence weather patterns thousands of miles away. The magnetic field serves as a bridge between the geological and meteorological worlds, connecting processes that operate on vastly different timescales. The study of magnetic fields has also opened new frontiers in medical research. Scientists have discovered that some biological processes appear to be sensitive to magnetic field variations, though the mechanisms behind these effects remain poorly understood. The same magnetic sensing abilities that guide migrating animals might exist in rudimentary form in humans, influencing everything from sleep patterns to mood in ways we're only beginning to investigate. Magnetic therapy, while still controversial in mainstream medicine, continues to generate research interest as scientists work to understand how magnetic fields interact with biological systems. The key is distinguishing between legitimate biological effects and wishful thinking, a challenge that requires careful experimental design and rigorous statistical analysis. The quantum sensors that are revolutionizing magnetic field measurement are finding applications far beyond geophysics and space weather monitoring. These incredibly sensitive instruments can detect the tiny magnetic fields generated by neural activity in the brain, offering new insights into how our minds work and how various neurological conditions affect brain function. Medical imaging techniques that rely on magnetic fields continue to evolve, providing ever more detailed views of the human body without the need for invasive procedures. The same principles that govern Earth's magnetic field interactions are being applied to create more effective MRI machines and other magnetic imaging systems that can detect diseases in their earliest stages. Archaeological applications of magnetic field technology continue to reveal hidden treasures from our past. Ground-penetrating magnetometers can detect buried structures, ancient roads, and even individual artifacts by measuring tiny disturbances in the local magnetic field. These magnetic archaeological surveys have revolutionized our understanding of ancient civilizations, revealing entire cities that show no surface evidence of their existence. The environmental monitoring applications of magnetic field measurements are expanding as scientists recognize that magnetic signatures can reveal information about pollution, contamination, and ecosystem health. Heavy metals and other pollutants often have distinctive magnetic properties that can be detected and mapped using sensitive magnetometers, providing a cost-effective way to assess environmental damage over large areas. Marine biologists have discovered that many ocean creatures, from whales to sea turtles to salmon, rely on magnetic navigation for their epic migrations. As human activities continue to alter the electromagnetic environment of our oceans through underwater cables, shipping traffic, and coastal development, researchers are working to understand how these changes might affect marine navigation systems that have evolved over millions of years. The rapid movement of Earth's magnetic North Pole towards Siberia has practical implications for navigation systems around the world. Airports must regularly update their runway designations, which are based on magnetic compass headings, to account for the shifting magnetic declination. The accelerating pace of this polar motion has forced more frequent updates than ever before, highlighting how dynamic our supposedly stable magnetic field really is. Indigenous knowledge systems around the world contain sophisticated understanding of magnetic phenomena, often encoded in traditional stories and navigation techniques that have been passed down through generations. Arctic peoples have long recognized the connection between auroral activity and weather patterns, knowledge that modern science is only beginning to appreciate and understand. The integration of traditional knowledge with modern magnetic field research is revealing new insights about how these invisible forces have influenced human cultures throughout history. Ancient stone circles, mysterious magnetic anomalies, and traditional navigation techniques all reflect humanity's long relationship with Earth's magnetic environment, even when the scientific basis for these phenomena wasn't understood. As we look toward the future, the study of magnetic fields continues to evolve and expand into new realms of discovery. Quantum computers, which rely on precise control of magnetic fields at the atomic level, may eventually revolutionize our ability to model and predict magnetic field behavior. These quantum simulations could provide insights into magnetic field generation and dynamics that are impossible to achieve with classical computers. The search for room temperature superconductors, materials that could conduct electricity without resistance at normal temperatures, could revolutionize magnetic field technology. Such materials would make it practical to create powerful magnetic fields with minimal energy input, opening possibilities for everything from magnetic levitation transportation to more effective magnetic shielding for spacecraft. Fusion energy research continues to benefit from our understanding of magnetic field dynamics, as scientists work to create the powerful magnetic bottles needed to contain the incredibly hot plasmas required for nuclear fusion. The same processes of magnetic reconnection and plasma instability that occur in Earth's magnetosphere provide crucial insights for designing more stable and efficient fusion reactors. The growing field of astrobiology has identified magnetic fields as one of the key factors that determine whether a planet can support life. As we discover more exoplanets and develop techniques for studying their magnetic environments, we may find that magnetic protection is even more crucial for habitability than previously thought. Space telescopes designed to detect the radio emissions from exoplanet magnetospheres could revolutionize our search for potentially habitable worlds. The presence of auroral radio emissions from a distant planet would indicate not only a magnetic field, but also an atmosphere dense enough to support auroral displays, suggesting conditions that might be favorable for life. The philosophical implications of magnetic field research continue to evolve as we deepen our understanding of these invisible forces. The realization that we live within a protective magnetic bubble has changed how many people think about Earth's place in the cosmos and our responsibility as stewards of this magnetically shielded world. Educational initiatives around the world are working to increase public understanding of magnetic fields and space weather, recognizing that future generations will need to be scientifically literate about these phenomena as our technological dependence continues to grow. Students are learning to monitor real-time space weather data and understand how magnetic storms affect the technology they use every day. The artistic community has embraced magnetic field visualizations as a new form of scientific art, creating beautiful representations of invisible forces that help people appreciate the hidden beauty of our electromagnetic environment. These artistic interpretations serve as bridges between the scientific and aesthetic appreciation of magnetic phenomena. Tonight, as you settle into the peaceful embrace of sleep, you're surrounded by the culmination of billions of years of planetary evolution and centuries of human discovery. The magnetic field that protects our world is working silently in the darkness, deflecting cosmic radiation, guiding charged particles toward the poles where they create gentle auroral displays, and maintaining the delicate electromagnetic balance that makes life possible on this small blue planet. Every heartbeat, every breath, every dream that carries you through the night is made possible by invisible forces that connect the deepest parts of our planet to the farthest reaches of space. The magnetic field that cradles Earth is more than just a scientific phenomenon. It's a testament to the elegant way that natural forces can create protection, beauty, and the conditions necessary for consciousness to emerge and contemplate its own existence. As you drift off to sleep, carried by the gentle rhythm of these words and the comfort of knowing that you're protected by forces far greater than yourself, remember that you're part of an extraordinary story. You're living on a planet that developed its own electromagnetic immune system billions of years ago, a world that learned to protect itself from the harsh environment of space through the simple elegance of moving electric charges in its molten core. The magnetic field that surrounds you now has been Earth's constant companion through ice ages and warm periods, through mass extinctions and evolutionary radiations, through the rise and fall of countless species. It will continue its patient work long after we're gone, maintaining the invisible shield that makes this world a haven for life in the vast, often hostile cosmos that surrounds us. Sleep well knowing that you're cradled not just by the comfort of your bed, but by invisible fields of force that stretch from the Earth's core to the edge of space, creating a protective embrace that has made all of human history, all of our dreams and discoveries, all of our love and wonder possible. In the gentle darkness of night, Earth's magnetic field continues its ancient vigil, a silent guardian ensuring that morning will come again to our magnetically protected home among the stars.